Thank you so much. So first of all, I'd like to thank all the organizers for this very kind and arrangement. So certainly it's a great privilege and honor for me to speak here. Okay. So today, I would like to report and also survey some recent work on the validity of so-called steady Prandtl layer expansions. Okay. So let's begin with a two-dimensional steady Navier-Stokes equation. Okay. So this is an equation people usually say for describing a real fluid. Okay. So here in 2 dimensions, okay, so we have two velocities, 2 directions of velocities to describe this fluid. So one is, I will call that u, which is the horizontal velocity. Okay. And also we have a v, is so-called normal velocity. Okay. So this depends only on spatial variable x and y. Okay. So we're in 2-dimensional case. And the region I'm considering is part of the first quadrant. Okay. So this is my x and y. Okay. So I'm considering here. And moreover, there is a boundary here. Okay. So this is x equals to L. Okay. So this actually is the region I'm considering this problem. Okay. So we can imagine a 2-dimensional fluid, okay, passing through this region, right? Passing through this region. Okay. So here, u is the horizontal velocity, while v is the normal velocity. Okay. And we have a pressure. Okay. So P denotes the pressure. Okay. So this is the left-hand side of the equation. On the right-hand side of the equation has to do with so-called dissipation. Okay. Dissipation. Okay. So we have second-order derivatives of the velocities. Okay. Second-order velocity. Okay. Here, there's a very important physical constant, which is playing an important role in our talk. Okay, so this is the coefficient in front of these second-order derivatives. I will call it as a small parameter epsilon. Okay, so epsilon here. So epsilon represents the so-called viscosity. Okay, viscosity. In a more general context. Okay. So this epsilon can be also viewed as the reciprocal, okay, the reciprocal of so-called Reynolds number, okay, Reynolds number, okay. But in any case, in our talk, we will treat epsilon as a small parameter, and we try to study the behavior when epsilon go to 0, okay, epsilon go to 0. So this is a small parameter. We will let it go to 0 in the end. So this equation is a 2-dimensional steady. Okay, steady means there's no time. Okay, there's no time. So this is the setup. So we start with a steady flow, okay, 2D steady real flow. Okay, and in order to solve this, so usually people have the incompressibility condition. So divergence of the velocity field is 0. So this way, we have 3 equations, okay, for 3 unknowns, u, v, and p. Even though there's no equation for p, but under this condition, you can show that in general you can solve. You can solve for p. Okay. So there's 3 equations for 3 unknowns. Okay. So this is the setup, right? This is the setup. So this is the equation should be satisfied within the region, within the region. Of course, in general, you need to have boundary conditions in all physical situations. Okay? So the important, one of the classical boundary conditions for a real fluid is so-called non-slip boundary conditions. Okay? So the meaning of a non-slip boundary condition means that the fluid should travel exactly, at the boundary, should be exactly the same as the velocity of your boundary, Okay, so this is the meaning of non-slip boundary condition. Okay, so here let's assume on the bottom boundary, bottom boundary, let's assume the boundary travels as the speed of a constant speed. We'll call it u sub b. Okay, so here, this is bigger than 0. Okay, bigger than 0. And then we want to assume that v is also equal to 0. The normal direction should be 0 because the boundary we assume is just moving this way. Okay, just moving this way. Okay. In the classical case, this ub should be 0. ub should be 0. That means you have a motionless plate, okay, motionless boundary. Okay, so this is our setup. So for the rest of the talk, we always will make this an important assumption, okay, so that a plate actually is moving. Okay, so this, so even in the context of a steady flow, the Navier-Stokes theory allows a constant velocity flow. For instance, if you consider so-called Couette flow is one of the simplest and maybe one of the most well-known flow. Okay, so basically you have two plates and then one plate is moving, okay, at a constant speed. Okay, so Couette flow is a well-known steady solution to the Navier-Stokes equation. There, the upper boundary velocity is constant. Okay, it's constant. So this is certainly is classical. Okay, classical. So this is the setup of our problem. Okay, setup of our problem. So the question we're interested in is what will happen when epsilon go to 0? How can you describe the solution of this equation, or in some sense real flow, when the Reynolds number is very, very big, or the viscosity is very, very small? Okay, very, very small. So this is the question we want to address. Okay. So formally, if we just let epsilon go to 0 here formally, so that this will be 0. Okay, this will be 0. So then we arrived at another, maybe even more famous equation. Okay, so this is so-called inviscid. So now when epsilon equal to 0, there's no viscosity. Okay, so people usually say this is a inviscid limit, right? So in this inviscid limit, so basically formally you get a 0 here. You replace 0 here and 0 there, and this you keep, right? This is you keep. So in the limit, so you will arrive this so-called Euler equation. Okay, same notation, right? Same notation, same physical meanings. Okay, Euler equation. Well, Navier-Stokes equation was discovered, I think, around 1840, around 1840s also. Euler equations are certainly even before, right? So Euler equation was discovered, I think it's 17-something. Okay, so Euler equation certainly is, was among the first equations, okay, encountered by mankind. Okay, so this is a certainly very, very famous equation. Okay. So Euler equation has this form. Okay, so we would hope that this solution should indeed converge to the Euler solution of this equation. But actually, if you're away from the boundary, this in general more or less is true. But at the boundary here, there's some problem. Okay, there's some problem. The problem is that, unfortunately for the Euler equation, we cannot impose these two conditions anymore. These two conditions we cannot impose. In particular, we can only impose the normal derivative to be 0. This follows from general physical principle. This is so-called non-penetration boundary condition because there's nothing going in or out of the boundary. So this indeed is required. And it turns out for the Euler equation, okay, this condition is enough to determine the Euler flow. So in other words, if I insist on this, then there's no way I can be sure the horizontal velocity on the boundary is exactly match up with this UB, which is our Navier-Stokes solution. Okay. So in general, there is a typical mismatch between the horizontal velocity at the boundary of the Navier-Stokes flow and the Euler flow. Okay. By the way, Euler flow usually people refer as an equation for describing an ideal flow. Okay, ideal flow. So indeed, there is a mismatch between a real flow and an ideal flow. Okay, ideal flow. So throughout this talk, we want to consider some simpler Euler solutions. Okay, so those solutions are well known. They are called parallel flows or shear flows. Okay, so they are of the form of a horizontal velocity only depends on the y coordinate. Okay, and then the vertical velocity is identically 0. Okay, identically 0. It's very easy to see if you plug this back into the Euler equation. You can see that this is indeed satisfied, and also satisfy this non-penetration boundary condition. So this is a good flow, right, in our context. However, in order to highlight the difference between the Euler flow and the Navier-Stokes flow, we're going to assume that in general, okay, so this at the boundary, this Euler flow has a different speed, okay, different speed than the from the Navier-Stokes flow. So this is our setup. So we are going to consider basically a shear flow, Okay. It is quite interesting actually to see the difference between a real flow and the ideal flow. For instance, these solutions are so well known for Euler flows, right? This is any profile, you can see this is a solution. However, this in general is not a solution for the real flow. So this is not a solution to this. Okay, only very, very few specific profile. One of them is the co-ed flow profile of this, or another one is so-called parabolic flow, right? So so only those two flows make this equation satisfied. That also tells us that actually there is a big difference between real and ideal. Okay, real and ideal. As a matter of fact, it's still an open problem to see whether or not you can construct some solutions of the real flow near those steady states. Okay. So there is a mismatch. Okay, so we can see there might be some problems. Okay, for the convergence when epsilon go to 0. Okay, so indeed, how to describe this difference, how to resolve this mismatch, was considered by Prandtl in 1905. Okay, so his idea is he thinks that there will be a very sharp transition, okay, of the order of a square root of the viscosity. Okay, there's something drastically happen. So when you more or less inside, you are more or less approach to Euler flow. However, but when you undergo a sharp transition, right? Sharp transition from oil flow to the never-stop flow near the boundary. So this was his idea. Okay. So in order to facilitate his coordinates, so what are we going to do? So we're going to reformulate his theory in his coordinate system. Okay, in his coordinate system. So I'm going to make a change of variable. X stay the same. So now I'm going to use a rescaled variable. Little x, which is the same as big X as before. And then little y is I rescaled. So basically, I'm going to look at, I will blow up this region, which is the thin layer region. Okay. Since I am considered the quadrant, y is unbounded, this is okay. So the region won't change. Okay. So I'm going to try to reformulate, rewrite everything in his coordinate. Okay. So if you do that, then this will be the equation. This is very easy. Okay. You just do change of variables. Okay. So this is the real flow in the new coordinate system. Okay. So Prandtl's theory amounts to be the following assertion or hypothesis, right? So he claimed that when epsilon go to 0, when epsilon very, very small, then the original real flow can be decomposed into the Euler flow. So here I have a square root of epsilon because I used the new variable here. This is the old shear flow we had. Okay, there's shear flow. So in this context, okay, in this context, so in the context of shear flow, okay, so Prandtl theory just asserts that the real flow can be decomposed into Euler, then plus something which is called boundary layer flow. This was invented by Prandtl, right? So where Prandtl layer equation is given by this, okay? So he has by identifying this this square root of epsilon scale, he can derive another equation. Okay. Okay. He can derive this equation of the following form. Okay. You still have the divergent free, but everything now is in the rescaled variable. In particular, the xx derivative drops out. Okay. So there's only one. So this equation in PDE language, we call it a parabolic type of equation. Okay, so if you view x as a time, okay, this equation has similar features, okay, as the heat conduction. Yeah. Yeah.
You didn't explain what are the boundary conditions at x equals 0 and x equals.
Oh yes, yeah, I will, yeah, later, yeah. Okay, so yeah, okay, so for this problem, the Navier-Stokes equations, when we're written on this form, in PDE language is so-called elliptic type. So for elliptic type of equation, we need to prescribe boundary conditions. Okay, so we have to impose some boundary conditions on this side and this side. This side I don't want to touch because this is the key central question of the problem. Okay, so for these two boundary, we're going to try to propose some boundary conditions for our method to work. So here we do not pay too much attention because the central question we want to understand is here. Okay, I will specify the boundary condition later on. Okay, so so this is a parabolic equation, and so this in this rescaled fashion, this actually in the original scale, this represents the sharp transition. Okay, in this one, yeah. So this is his theory, basically. Okay, he hypothesized. So this should be true. Okay. Well, Prandtl theory is highly regarded in the fluid community, right? there are several reasons. One reason I think is really it connects up with these two important theories, okay, of Euler and Navier-Stokes. Okay, so my understanding of the theory for fluids is that somehow people beginning when they discover Euler, a lot of people studied Euler equations, finding a lot of special solutions, exact solutions, and but however, people haven't. I mean, in science application, people do not follow the Euler theory that much. Okay, one of the reasons by doing experiment, people realize, in particular near the boundary, for instance, right, the Euler theory is not really that precise. Okay, so Prandtl theory somehow bridge these two theories. Okay, bridge the theory. So normally people consider usually Navier-Stokes is pretty, well, I wouldn't say accurate, but certainly it's a very, very good model, fundamental model for the fluids. Okay, for the incompressible fluids. So so Prandtl, the first significance of Prandtl theory certainly bridge the gap, right? Really, I mean, if you're interested in a problem when the velocity is very, very small, which is happens a lot. Okay. So for instance, in airplanes, a lot of things, even though the physical viscosity might not be small, but because of the speed and the scale, the Reynolds number is large. Okay, so this is the first significance, right? So it's really bridge up the two important theory. Okay, another importance is a somewhat practical one. Okay, somewhat practical. As I said before, when you try to compute this steady flow, is elliptic, right? When you have an elliptic equation with this small coefficient here, it's very expensive to compute. Very expensive to compute. However, if I know this is true, right? If I know this is true, then Euler I can compute differently. Then the only thing I need to compute is this Prandtl equation. The Prandtl equation here is as I said before, is a parabolic type of equations. So usually we solve in PDE, parabolic equation, we solve initial value problem. Okay, you view x as a time step. Okay, so this equation much more easier to solve. Okay, much more easier to solve than the elliptic equation. So in fact, for a long time, people are using this try to compute a flow. Okay, so to simulate a flow. Okay. I'm not sure about now, because now the computer is so powerful, right? So probably people are not doing that, but at least for a long time. Okay. So the third component is Prandtl theory. I think is quite a seminal contribution because actually I think he was the first to really make the rescale of the equation and then identify this type of new boundary layer equations. So after his work, then there were a lot of boundary layer theory, right? Came out to model systems that basically have two very, very distinct scalings. Okay, distinct scaling. So this is really even theoretically, it's really, really important, right? Really important. As a matter of fact, one of the most important exact solution of the Prandtl's equation, this is so-called the Blasius flow. Okay, so Blasius flow, my understanding is it match up very well with the experimental data, right? The profile, the stability profile. So certainly it's a very well-known theory, okay, in the fluid mechanics. Okay. Okay, so now we try to be more precise. So the question is whether or not, as a mathematician, whether or not we can somehow show this expansion is true, or in other words, whether or not we can validify Prandtl's theory from a rigorous mathematical viewpoint. In other words, whether or not you give me a Navier-Stokes flow, whether or not you can show this is valid, okay, whether or not this is valid. So this is a important open problem still now. Okay, so we would like to address this problem in the following. So as for this complete problem, and this is still open. Okay. Of course, it's important, right? Because this can give a theoretical foundation for the Prandtl theory. Okay, Prandtl theory. Yeah. Well, there have been a lot of mathematical work on the general area of the Prandtl theory. Okay, due to its importance, I would say starting from Olenek, right? There were a lot of work, and then there were many people have worked on that. But I would say most of the work concentrate on the solvability of the Prandtl equations, whether or not you solve the equation. So our emphasis is different. We want to assume Prandtl is already solved. Our perspective is whether or not you can show the decomposition is correct. So for us, the oil flow is known, and then we assume the Prandtl flow is also known. Okay. So, so most work are with regard to the solvability of a Prandtl equation. There are only few addresses the problem of validity. Okay, validity of this expansion. Okay. So, in particular, Sammartino and Kavlish show the validity of the unsteady case. That means you have time dependent. In that case, for analytic data, if you have an analytic initial conditions, then they can show after a short time, you have the validity. Okay. And recently, Masmoudi and Joravare, they could also lower the lower the class to so-called Gervais class. Okay, Gervais class is okay. Yeah. Of course, these two classes are still a little bit restrictive from application viewpoint. Okay, so so the question really is whether or not you can show the validity in the time-dependent case. Okay, with a finite number of regularity, let's say Sobolev space. Okay, so this is still open. This is still open. As a matter of fact, my feeling is that this in general might not be true. Okay, so since we have some specific examples which can show that at least the expansion is not right. Okay, at least the expansion is not right. Okay, so so this is the unsteady case. Okay, so we want to study the steady case because most of the literature in the fluid mechanics are really are about steady case, because even though unsteady are more important, but for a flow, for instance, when we study the flow near the airplane, then usually apart from takeoff and landing, right? So most of the time you can still approximate flow as a steady flow. So we want to focus on the steady flow. This is the first region. Second region is, of course, because we want to stick to the original Prandtl's setup, right? So the Prandtl theory was within the steady flow. Okay, steady flow. Okay. So we want to study the steady flow. Okay. So here we want to reformulate this problem a little bit. Okay. So what we want to do is some weaker version of the Prandtl's conjecture, okay, or hypothesis. So what we're going to do, so here Prandtl asks whether or not the Navier-Stokes flow can be decomposed into the Euler and Prandtl, right? So now actually you can keep on going. You can fill in more so-called Prandtl layer expansion. So this you can. So this is more or less a zeroth order in epsilon expansion. Now you can go on to first order, and then second order, and third order. You can go on forever. Okay. So we want to try to show whether or not this expansion is valid or not. Okay. This expansion is valid or not. Okay. So here we need to insert some higher order expansions. Maybe go to one more. Okay, this is for technical reasons. So we have one more, but the important thing is that all these expansion in front, they are well behaved. we can compute easily, okay? Not easily, but we assume we know, okay? So these are okay, these are no. So in order to show Prandtl's theory is valid, the only thing we need to control is the remainder. So suppose I can show these are the remainder of the Navier-Stokes flow. If I can show, for instance, if these are bounded, uniformly bounded in epsilon in some fashion, then Prandtl's theory is okay, because now this is going to 0, epsilon go to 0, right? And then this is the main part. That's exactly what Prandtl claimed. Okay. So the key is to control the remainder, which will be a nonlinear equation, satisfy a nonlinear equation. Okay. So now, so here's the problem. Okay. So whether or not you can show the remainders, okay, remainders will be bounded. Remainder will be bounded. So the mathematical setup would be what do you mean you want to verify this problem? Because this problem is an elliptic problem. Okay. So basically, our assumption should be here. If we look at this chart, right? This is a formal expansion. We want to say that the remainders, okay, u epsilon, v epsilon, are somehow bounded here and bounded here. The question is whether I can show it's also bounded inside. In other words, we want to assume Prandtl's theory are valid, expansions are valid on the side, okay, on the boundary. The question is whether I can show they are valid interior. So this is the mathematical question we want to ask. Okay, mathematical question we want to ask. So here's the theorem. Okay, there's a theorem with Nguyen. Okay, Nguyen. So the condition is on the remainder. Okay, the condition is on the remainder. Okay, remainder. Okay. The remainder here we cannot change anything. Okay, so the remainder and also the approximation make sure such that you always this part for the Navier-Stokes equation always is non-slip. Notice that because I'm considering this is u is I've already taken out the moving velocity from the Prandtl's approximation and also from the Euler, right? So this remainder really exactly have these homogeneous boundary condition equal to 0 here. Okay, this is precise. I cannot change anything. Okay, this is a given. This is the hardcore of the problem. Okay, so this is a given by the problem. Okay. Okay. And then, what are the boundary conditions on the side? What are the boundary conditions on the side? Well, the boundary condition on the side, we're going to assume that the boundary condition on the side, on the left-hand side, is some function is bounded function given. So when you have a flow, okay, by the way, okay, when you have the physical flow, there's no when the flow is moving, right? There's no appropriate boundary condition on both sides. Okay. So there's no, okay. So what we want to say here is at this side we know is somehow it's given, right? It's given or bounded. Okay. On the other side, we have, so this is like a so-called Dirichlet boundary condition. And this, on the other side, when x equal to L, we assume that the pressure, the remainder of the pressure remainder, okay, minus this funny combination is known, or is bounded. And here, this again, this is a funny combination of derivatives is also given. Okay, so when these are 0, these conditions are well known. It's so-called Neumann boundary condition for the Navier-Stokes flow, or people also say stress-free boundary condition. Okay, but here this is not homogeneous. Okay, this is not homogeneous. So then assume this is true. This condition more or less saying you're moving. Okay, you're moving here. The plate is moving. Okay, so this is basically the main consumption. Main consumption is the plate is moving. Okay. So then we have the following estimate. Okay, we have following estimate. Okay, so let me denote the weighted gradient is like this form. Okay, the important thing is for the y derivative, the normal the normal derivative. This is order 1. There's no epsilon. Here, there's an order epsilon, so that you cannot control this quantity. So we have order 1 in y derivative. So then there exists a short L. There is a L sufficiently small so that we have the following estimate. Okay, we have formula. So indeed, the remainder is bounded. Remainder is bounded in some norm, in some measure, measure. Okay. So here, the most important thing here to realize is that when you have this, at least the y derivative of u epsilon is order 1, right? Order 1. And then here, at least the y derivative is order 1. So once you have this estimate, then you can translate into the original coordinate. So then you will have u itself indeed is decomposed into this Euler plus the Prandtl. Similarly here, the normal derivative of v is decomposed with the Prandtl because Euler now is 0, right? And then there is a small correction from the next order of Euler correction. This is a well-known effect. Okay, this is a well-known effect in fluids. Okay, so you can show this is true. So indeed, this way you verify that the Prandtl theory is correct. Okay.
So how many higher order terms you assume exist? 1 or 2?
Oh, for technical reason, we assume 1. Yeah.
Okay, so you need assumptions for those first order terms to
yeah.
exist.
Oh, yeah. We need to assume. Yeah. So we were saying.
For instance,
yeah.
You know, from the equations you wrote,
yeah.
I have a feeling that one needs the shear flow to be convex in y. I know that you have a V1 epsilon, a V1 Euler.
V1 Euler, yeah.
You need something about signs.
Yes, exactly.
Because it's like a zero order terms on the end.
Yes, exactly. So the most important assumption is actually the flow for the, so let me try to draw a picture. The flow for the Prandtl layer, right? From the Prandtl layer is something like this. So it's going something like this. Some kind of flow like that. Yeah, the profile is something like that. And then, so only the first zeroth order term is nonlinear. Afterwards, all linear.
Sure.
Yeah. So.
Still, you need to be able to solve them.
Oh yeah. Absolutely. Yeah. Yeah. Oh yeah. That actually, yeah. Yeah. Even in the static, absolutely. There is an important condition actually. One need to pose. Actually, I will comment on that. Yeah, I will comment on that. Okay, so I want to make some comments. So, okay. Oh, when you have something moving, okay, so this has occurs. This phenomenon occurs in many different physical contexts. For instance, these are so-called shear layers, right? So you have two uniform flow in. Okay. So when you have a viscosity, then you cannot use the so-called Kelvin-Helmholtz. You cannot use Euler. It's at least debatable, right? So then there's a lot of so this you can view. This is like a moving Navier-Stokes flow. Okay, and then in our estimate, unfortunately, this L will shrink to 0 if the velocity is shrinking to 0. So as for now, the classical case, if you have a motionless case, is still out of reach for our theory. Okay, for our theory. So yeah. Okay, so let me first just try to illustrate the main difficulty. Okay, so the main difficulty is quite clear when you try to work on a little bit on the Prandtl type of equation. The problem is a lack of a priori estimate. So one standard way to start the process is we look at the energy estimate, right? Energy estimate for the Euler equation, Navier-Stokes equation. Then energy in this context, you get something like this. Okay, so you have this more or less order 1 because this is order 1, right? At least some part is order 1, and then this is order epsilon. Okay, for the normal velocity from the energy estimate, the most you can get is order epsilon estimate. Unfortunately, then if you look at the right-hand side, this is coming from the convection terms, right? So this is depending on the profile here. US more or less is a combination of the Euler plus the Prandtl, right? Euler plus the Prandtl. This is order 1 quantity. Order 1 quantity. So now you want to control this by the left-hand side in order to close your estimate. You can see that U part is okay because I at least have a Uy is order 1. So this is more or less say is order 1. But we stuck with V. Because V, the only thing we get is order epsilon. Okay? So this term is out of control. It's out of control. The best we can say is then this is bounded by some L times, well, we need this, right? This is order 1. Okay? This is order 1. We need this order 1. This is a very typical difficulty when you try to play with the boundary layer problem. Okay? So this is no matter in what coordinates, you always encounter this huge terms which is out of your control if you just use energy. If you just use energy. This is a very typical examples. Of course, in this context, in this coordinate system is just presented in this form of the difficulty. So we need a new estimate. So this energy estimate is not good enough. Okay? Definitely not good enough. So the key new contribution is we discover a new estimate for the normal derivative, order 1. Okay? So this estimate is the follows. Okay? So we found a different estimate, which is somehow is in some sense is orthogonal to the energy estimate, which takes the form of the order 1 derivative of V is bounded by order 1 derivative of U. Okay? Suppose I will have this estimate. If we have this estimate, now I can plug this back into the energy estimate I had before. Right? So then this is more or less I have a same U and same U here. Now if I assume L is small enough, I can absorb this guy on there, so that I'm okay. Okay, so this is the key estimate. Okay, this is the key estimate. I will try to illustrate at the end. Okay. So our proof actually was for the homogeneous case. Our proof is basically assume these are homogeneous for simplicity. Okay, but once you give a general non-homogeneous one, it's the same. Okay? As long as you're willing to assume higher regularity. Okay, so now I would like to state some extensions. Okay, some extensions. The first extension is a rotating disk. So let's consider a different geometry. Okay, so we have a rotating disk, and the flow, oil flow, is going like this. Okay. So this is a situation. Okay, this is again a classical example in fluids. Okay. So we have a rotating disk, and with a constant speed, right? So this look like our moving plate, right? And then of course we have a real flow, Navier-Stokes flow, which is again has the non-slip boundary condition, right? And then we could have a shear-like Euler flow as well in this case. Okay, in this case. So then. My PhD students, Séminaire, Iyer, could show that now the Prandtl expansion is still valid. Okay, still valid. Okay. So the new ingredient there is certainly you have a curvature effect, right? Curvature effect, even though it's a epsilon order effect, but that will play present new difficulty for the weighted estimate in the horizontal direction. And also, there is a new estimate for the pressure. Okay, and so this is this is the result there. So next theorem is about so-called global validity in space. Okay, so we know that when L is small, then we can show the validity of the Prandtl layer theory. The question is, clearly when this mismatch is small, the L can be big. But the question is whether or not you can move on forever. Okay, whether or not the Prandtl layer theory is valid globally. Okay, this is not quite obvious because in fact most the physical situation shows the otherwise. If you look at the experience, many of them show that after a while the Prandtl layer will become detached. So then the Prandtl layer theory should be invalid. Okay, after a while, I meant after some distance. This is well documented in the experiment. Okay, but nonetheless, Semir Iyer could show the following. Okay, So let's assume the Euler flow is just a constant. This is a technical assumption. I think you can be more general, but for boundary layers, most people just take this constant, right? As long as they're different from the Navier-Stokes flow. So then assume that somehow the mismatch is small. Suppose the mismatch is small. Okay. Then Prandtl layer is indeed valid globally in X. So there's no detachment. You cannot have a detachment forever. Forever. Okay. I thought this is quite a remarkable result because this is actually from physical viewpoint, right? So this is really the first result tells you, the boundary layer theory is really okay, right? Really okay forever, right? And also, mathematically, his work is quite a tour de force, okay? So in order to really prove this result, you really need to first study the decay. So the important thing is the decay when X is large. Decay in X. The decay, you have to study the decay very, very carefully. Even though he got all the sharp decay he could have, but still there's a, key difficulty where exactly the decay is somehow at a critical Hardy inequality level. So exactly we get something like this, but this cannot control this. Okay, this is exactly the critical Hardy. Okay, this is not true. This is false. But unfortunately, we would love to have such kind of an estimate to closely estimate. So he designed a higher order estimate to accomplish this. Okay, it's a very sophisticated scheme. Okay? So it's really quite a solid work. As a matter of fact, actually, I try to simplify the arguments many times, but still, I mean, right now the paper stands more than 100 pages. Just so complicated. Okay. So the new mathematical difficulty, there are several quite annoying mathematical difficulties. Most of them have to deal with the case that we're in a corner domain. So then, unfortunately, the elliptic theory is a pain to work on the regularity. So that also means we cannot go very high regular. We have to work on something with low regularity. Okay. So the key estimate is the following for the normal velocity. This is the key estimate. This is the estimate we can get, order 1 estimate for velocity. So basically, you look at this equation, basically. This is more or less your equation on the linear version. So this US is given, right? This is the Prandtl one. Prandtl plus the Euler, right? This is the main contribution from the leading expansion. All the others, when you are willing to expand higher order, then the nonlinearity doesn't matter. The key problem is your linear estimate. Okay, but even for the linear estimate, you don't have a good estimate. Okay, so here you have this is more or less given. Okay, and this is more or less given. So you are looking at the equation like this. Okay, so the question is how do you do a priori estimate? So when you do energy estimate, this is the vorticity form. For energy estimate, basically what you do is you multiply by the so-called stream function. The question is whether or not there are some other estimate you can do. So now you do not want to spoil the boundary condition. Okay, that's the key thing. You want to make a multiplier which is preserve the boundary condition. Okay, so we found one multiplier exactly of this form. So V divided by US. Okay, if you do that, you see this somehow will drop out. This is why I'm saying this is more or less orthogonal to the energy estimate, because when you multiply by phi, the main contribution is coming from here. The positive quantity is coming from your dissipation. But when you multiply by V here, then this term, by the nature of the boundary condition, basically drops out. Basically nothing. So you're really talking about this more or less a Rayleigh equation. Okay, Rayleigh equation. So the question is, when you do this, whether or not you can obtain some positive estimate for your V. So this is entirely coming from the part from the convection term. Okay, this is because you have this non-trivial convection term. This has an order 1 contribution. So if you multiply, the important thing to realize is that for this Rayleigh equation, we have a positivity. If you multiply by this, we'll have a positivity here. Why is that? Well, because here we know US somehow exactly is a solution. If V equal to US, exactly the solution of this Rayleigh solution. One of them at least. So Rayleigh solution always have a kernel. That's the annoying part. You have a kernel, then it's hard to get a positivity estimate. Okay. So now, if I multiply by this, so why this is okay in this case? Because US, V cannot be US. Why? Because my key assumption is that US is moving. So V has to be 0 at the boundary. That's the perturbation. That's the remainder has to be 0. So this somehow is excluded. That's the reason why this operator can be positive. Okay. So this operator is positive. This also plays a key role when you try to solve the the approximation. It's the same structure. So this will give you the estimate of this order 1. So then that's the end of the story. And then you can see why our result fails for the classical case, because exactly this at this point, right? So at this point we cannot do. Now we're still trying hard. You definitely need more new estimate, right? In order to solve the classical case. So I think I will stop here. Thank you very much for your attention. Yeah.
Thank you very much.
Yeah,